All right, in 4 dimensions, we're going to have 4 fundamental theorems of calculus. The first one is just going to be the F.T.C. for line integrals. It's exactly the same. It holds in any dimension. So we're going to have the integral of df is equal to f of b, if you like, or f of b minus f of a, if those are the endpoints, or rather, let's do it a little bit more sophisticated. The integral of df over an interval I is f evaluated at the boundary points of I. All right, that is our first fundamental theorem of calculus in 4 dimensions, where now df is equal to, I'm using x, y, z, w as my 4 coordinates, so df dx times the differential of x, df dy dy plus df dz dz plus df dw dw. The second one is the one I call the 4D Stokes Theorem. And that's because it has to do with rotations. I will state it for you, but it is quite nasty, and there isn't a really convenient way I've found to express it in vector form. Alright, so this is our second fundamental theorem of calculus in 4 dimensions. It is disgusting, as you can tell, but it's actually fairly intuitive what it means. I claim that this is the natural generalization of the 3D Stokes Theorem. Why is that? We have the integral over a surface in 4D space. Of course, it has to be orientable, so even though Klein bottles can exist in 4 dimensions, no integrating over Klein bottles. What we're going to get is that we have these scalar curls again, right? Only you think, okay, how many, if it's really measuring rotational stuff, well, 4 dimensions, there should be 4 terms, right? It takes 4 numbers to specify a rotation in R4. Wrong. You should check out the video on the dimension of the special orthogonal group that I put up. It takes 6 numbers, and that's why we would actually expect there to be exactly 6 terms in this integrand. And the deal is that rotation is fundamentally a planar phenomenon, and there are sort of so if you have n different axes, right? And you want to make a plane, then you're going to choose 2 axes out of those so that you'll get n choose 2 options, which is none other than n times n minus 1 over 2. And this is exactly going to be the the dimension of the rotation group. So that's the short version of that video. Okay, well, so this is rotation over a surface, and then we're saying that that's equal to this form integrated over the boundary, should that surface have a boundary. So I'm saying this really is the same thing as Stokes' theorem, it's just phrased a little crazier. Alright, so this is our third fundamental theorem of calculus in 4 dimensions, and once again it is a monstrosity. As far as intuitive explanation goes, of the 4 of them, I really believe this is the hardest one to explain. And that's because it involves a generalization of divergence that's not very intuitive, that works in 4 dimensions but not really in 3. I would like to point out that the divergence theorem is a special case of this, the 3D divergence theorem. If you were to set b equals c equals f equals 0, special case of this, you're integrating over a 3-dimensional volume, and we're saying that the 2-dimensional surface in 4-dimensional space bounding the 3-dimensional volume, if you integrate this over that surface, it's equivalent to this over that volume. Again, it's not super intuitive. It involves something similar to divergence, but a little bit different because of the nature of 4-dimensional space. It's weird. So you can think of 3-dimensional cross sections. So just like in 3-dimensional space, this is the best I can do as far as intuition. Just like in 3-dimensional space, you can cut it up into an infinite number of little planes, and we could look at the divergence in each plane, right? We could look at, is stuff going mostly out, or is it mostly coming in, right? This is what the divergence is. Or are we thinking of this vector field as being incompressible? Maybe it's neither, right? Maybe that divergence is 0 on the whole. But anyway, we think of that, and we can sort of cut them up and then add them all up together. Well, this is kind of going to be sort of the same situation, only you're going to be cutting up 4-dimensional space into 3-dimensional cross sections, evaluating a divergence on each of those, and then adding them all up in these four terms. And that is what this fundamental theorem of calculus in 4D is saying. So this is our fourth and final fundamental theorem of calculus in four-dimensional space. And what it's saying is that if you integrate over a four-dimensional hypervolume, this quantity, which is sort of an alternating divergence, you see the minus signs, this is equal to the bounding three-dimensional space or surrounding that four-dimensional space, that volume, hypervolume if you will, integrating this quantity over that. Now I claim that this is actually the rightful heir to the term divergence theorem, even though the last one contained it as a special case. And the reason is you can get rid of these minus signs by, instead of considering tangents, this is essentially considering tangent vectors or tangent higher dimensional things that aren't just one-dimensional or two-dimensional here. But you could, by considering normals, a normal to a volume, which is a weird idea, but a normal to a volume, you could get rid of these negative signs, and you would end up with the traditional statement of the divergence theorem. So I claim that this is the rightful heir because this is basically our four-dimensional divergence of a vector field. And I mean, if you look at the form, look at the 2D divergence theorem, right? Which was Green's theorem, but we stated it in a certain way. Del dot f ds is equal to integral of f dn, where this is the outward normal, right, over the boundary of A. And then the 3D divergence, we just take it up a notch, right? We're going over a volume of the divergence of f d, we'll just say dx here with the vector, is equal to the boundary of the volume, the surface bounding that volume, integrate the f d sigma, where d sigma is again an outward normal to the surface. So if we considered an outward normal to a volume, or I guess here, an outward normal to the volume, we get rid of those negative signs and it's gonna be the 4D divergence. And this is really intuitive. Instead of taking 3D cross sections and just looking at the divergences of those, like it was in the last theorem, in this one we're actually looking at a four-dimensional divergence. So perhaps you're wondering at this point, is there one fundamental theorem of calculus to rule them all? Is there one to find them? Is there one to bring them all and in the darkness bind them? To which I would reply, if you're having maniacal thoughts about world domination, you should probably see a therapist. But the answer is actually yes. Yes, there is one to rule them all. And it's called the Generalized Stokes Theorem. So, little background. We can think of dx as a function which assigns oriented length to 1D figures. So like if we have our x-axis here and we have some curve in the xy plane, imagine projecting this down to just this segment, and dx is the function that says project, you give me a curve and I'll project it onto this axis and give you a assigned length, oriented length. That means the direction matters. If you start here and end here, it's going to be a negative length. That's just the way it's going to work. Similarly, we can think of dx dy, which is also known as a two-form, a differential two-form, as oriented area. So that if we have something in the plane, again, to use the plane as an example, dx dy sort of measures the area of this thing once you orient it. Give it a counterclockwise or a clockwise orientation. Likewise, in 3 dimensions, you could take an area and project it down onto the x, or you could take some bendy surface and then project its image down onto the xy axis, or xy plane, sorry, and whatever this area is what this is spitting out in essence, all right? Only it's going to be sort of the infinitesimal version of that, because what we're going to get is what's called a variable form, which means you might have a function a of xy in front of it. This is what you end up integrating most of the time, but you can think of it without that as a constant form, in which case it really is lengths, areas, and volumes. Again, dx dy dz. It's going to give you an oriented volume. It's going to be the same story. over and over again. So this is a 1 form, a differential 1 form. This is an example of a differential 2 form. If it has the function of x and y out front, it's called a variable 2 form as opposed to a constant form. Then out here we have a 3 form, and you get it. You could keep going and form n forms, and you could see it as dx dy dz. Another way you might see this notationally is dx wedge dy wedge dz, although I don't really like that notation for several reasons, but never mind that right now. What we can do is, instead of saying that they're just a notational convention like they teach you in like Calc 1 or Calc 2, we're going to say no, they actually have an extremely important purpose, and we can do algebra with them. In fact, we can form a vector space with them if we want. So what we're going to do is we're going to define how they work. We're going to give it a set of algebraic rules. One, we can add them, so dx plus dy, this is fine. That's going to give you another 1 form. These put together is a 1 form. It's only 2 form if you have like a wedge product, right? Dx times dy. So that's okay. We're allowed to have dx dy plus dy dz. We can add 2 forms if you like, or 2 n forms even. What we can't do, however, we can't do dx plus dx times dy. Adding a 1 form and a 2 form doesn't really make sense. So we can add them as long as we use correct rules. The second thing we can do is multiply them. I told you a little bit about this a second ago. We can take dx wedge dy, and we can call this just dx dy if you like. I prefer it in this notation, whatever works for you. And a 1 form, take the wedge product, as it's called, of a 1 form and another 1 form, and you'll get a 2 form. Likewise, we could take the wedge product of dx dy and dz, and this is going to give us a 3 form. We have a 2 form times a 1 form, and that's totally okay. We can't add a 1 form and a 2 form, but we can multiply them just fine. And this is going to have an anti-commutative property, which is just that dx wedge dy is equal to the negative of dy wedge dx. And so that if you have omega, say, as an n form, and it may be a sum of things, right? Like dx plus dy plus 5 dz. This is still a 1 form, so I'm just saying a general form wedge another general form is going to be equal to the negative 1 to the power of, so if this is a k form and this is an h form, this is going to be negative 1 to the power k times h, and then times sigma wedge omega. So that's the way that multiplication with these works. And we have a couple other rules that we throw in there to make things work, which is that if you ever take the wedge product with itself, it's going to be 0. We're just defining that to be true. And we're also going to define how you take this d operation, also known as the exterior derivative, of a variable form. So you have a function out front that varies from place to place in space. So let's say it's a function of x and y, and then this is times dy, let's just say. So how do we take the exterior derivative of this? Well, we just define it to be dA times dy. And what is dA? Well, we know this by normal calculus. The differential of a function is just the partial derivative with respect to x plus the partial derivative with respect to y, where we have multiplied by the little differentials here. So this is going to be equal to dA dx dx plus dA dy times dy, and then times dy, or if you like, wedge dy. So that this term is actually going to be 0 because you have a dy wedge dy. And so that it's just going to be partial derivative of a with respect to x times dx dy. And we have just learned how to take the exterior derivative of a variable differential form. How about that? Additionally, differentiating like this, we can do d of a plus b dx is going to be equal to dA dx plus dB dx, etc. And of course, this operation is also going to be linear, so that if we have two numbers, not functions, but just numbers, real numbers, a and b, if we take the exterior derivative of AU plus BV, and U and V are variables, if you like, this is going to be A du plus B times dV. It's linear. Now, something that's really fantastic about this exterior derivative operator is that if you take d of anything, it's always going to be 0. D squared is always 0. This is a fantastic thing that allows you to do so much cool stuff. There's just this idempotence, if you like. What's important here is just that this corresponds to geometrically that the boundary of a boundary is 0. Have you ever thought about this? Suppose you have some surface, surface in space, let's do. So it looks like that, and then suppose it's cut off, and it has this loop at the bottom, and it's open. But other than that, it's like shaped like a bell, basically. So that is to say, the boundary of this surface, let's call it S, is this loop right here. But notice this loop is closed, meaning it has no boundary. It's because the boundary of a boundary is always 0. Likewise, the exterior derivative of an exact differential form is always 0. All right, so the natural setting of calculus in n dimensions turns out to be on these things called differentiable manifolds, which you can just think of as smooth, curvy objects in any dimension of space you want. They're smooth, they don't go off to infinity, they're always orientable, so no Klein bottles, we're throwing that out. And we want them to be compact, so like I said, they're not going off to infinity, and they're always differentiable. And this is really the natural setting for calculus. We can form calculus in n dimensions and say one fundamental theorem of calculus that contains every other one that's possible as a special case, using differential forms and differentiable manifolds. Are you ready? Let M be a compact, oriented, differentiable manifold with boundary. It's just to say that it's like the bell where it has that loop, although by a strange loophole in definitions, manifolds are also manifolds with boundary. Don't ask me about that. So even if it doesn't have a boundary, it can still qualify as a manifold with boundary. But let's not get into that. So, if M is a compact, oriented, differentiable manifold with boundary of dimension k plus 1, with boundary M as its boundary, which could just be 0, it contains that as a special case, and let omega be a differentiable, which is really a constraint on the variable function in front, differentiable k form defined on boundary M. Then the integral over the boundary manifold of the differential form omega is equal to the integral over the main manifold of the exterior derivative of the differential form omega. This cute little formula contains every possible fundamental theorem of calculus in any number of dimensions you like. Thus, this is one of the few times we can say that this is my final form, at least for the fundamental theorem of calculus.